Hi, everyone. Welcome to iCANX Talks. My name is Lan Fu, and I'm a professor from the Australian National University. And today I'm going to host this iCANX Talks with another great people you all know from iCANX Talks, Alice Zhang from Peking University. So this is today is the number 176 iCANX Talks, and we are great to have in celebration of the International Women's Day. It's a great pleasure we invited 4 leading female scientists in the field to join us tonight. So they are Professors Yanhong Tian, Veronica Augustyn, and Xiuyun Liu and Lingyan. And our first speaker will be Yanhong Tian from Harbin Institute of Technology. So I just give a very brief introduction of Yanhong, who is a tenured professor of the School of Material Science and Engineering, Harbin Institute of Technology, and national high-level talents of the MOE, and she's also excellent use of NSFC. She's currently the Vice Director of the State Key Laboratory of Advanced Welding and Joining. She mainly engaged in electronic packaging technology and reliability and flexible electronic variable sensor components. Yanhong is responsible for a number of key projects from different institutes and agencies. And also, she has published. She's also the chair and the committee members, the board members, various societies, institute, as well as journals. She has published over 300 papers in renowned academic journals and also the top-level conferences. She's also editor and co-editor of 6 books and won 4 professional and ministerial level awards of science and technology. So without further ado, Yanhong, the floor is yours. So I'll stop sharing. You can share.
Okay, thank you. Thank you for your introduction. I can share my window.
Yes, please go ahead.
Okay. Okay, hello everyone. I'm very glad to present here in this special day, and thanks Professor Alice Zhang for the invitation. I am Yanhong Tian from Harbin Institute of Technology, and I came from Harbin Institute of Technology, and my topic is about the micro-nano scale interconnection builds bridges from chips to devices. Actually, my research field is about the advanced manufacturing and fabrication. My topic will include 4 parts. Firstly, I will introduce briefly for the research background, and then I will introduce some macro interconnection technology in chiplets, and then 3-dimensional heterogeneous integration. And the first part, I will introduce some nanoscale interconnection used in the flexible electronics. Advanced technologies such as AI, IoT, AR, VR urgently require chips with greater computing power and high power efficiency because the Moore's law approaches its limit. Further improvement in chip manufacturing process will significantly increase manufacturing costs, while also facing issues of incompatibility and performance instability. Many experts and scholars have proposed that high-density advanced package can overcome the limit of the silicon-based devices and becomes an important solution in the post-Moore area. So the last year, the CHIPS law by the United States indicates that the government will invest heavily in the field of the advanced package and the heterogeneous integration to prepare the country leadership and it will also emphasize the importance of the building an advanced packaging ecosystem based on heterogeneous integration using chiplets, and also the chip will enhance the packaging talent development and manufacturing more packaging platforms. Actually, interconnection is a crucial technology in advanced packaging, serving as the bridge for communication between internal signals and systems within chips. Every advancement in advanced packaging owes its progress to development the interconnection technology. And the major chip manufacturers such as Samsung, TSMC, and Intel are actively structuralizing and deploying the advanced packaging solutions. For example, the Samsung X Cube use the copper pillar and the TSV technology to build the advanced package, and TSMC developed the CoWoS technology, and the Intel developed the Foveros chiplets. And MIT Technology Review has listed multi-chip package, that means chiplet package technology, as one of the top 10 breakthrough technologies of 2024, while simultaneously being recognized by the China Association for Science and Technology as one of the top 10 industrial challenges. Companies like AMD and Apple have proposed their own development plans for chiplets to seize the market opportunities. Compared to the system on chip, SoC chip, chiplets significantly enhance chip performance and reduce the costs without overly pursuing process refinement. Simultaneously, they make the integration of chiplets with different process parameters possible, which can greatly improve the yield rate. And heterogeneous integration technologies enable the integration of chips manufactured using different processes with different functionalities and from different manufacturers. High-density through silicon-wide TSV interconnections significantly enhance the overall functionality and operational performance and the integration level of the devices. And for the high-density advanced package, there are many challenges. For example, the packaging materials, interconnection materials, and the packaging processes, equipment, and reliability. And for example, in advanced package, challenges often involve tens of the thousands of macro bumps with ultra-fine pitch about 10 microns. And when the components during the service, the current density is very high, which will bring the electromigration failure. So based on the challenges and the background, some interconnection technology are very important in the advanced package, for example, the chiplets. So I will introduce some interconnection technology. Firstly, I will introduce three-dimensional package with nanocrystalline copper pillar. In high-density three-dimensional system package devices, the size of micro-bump interconnection has dramatically decreased. For example, the interconnection in this figure look like a hamburger. Actually, the size of this interconnection is only about 100 microns. and the pitch is about 200 microns. And additionally, during the package process, the chip will undergo the several reflow process, and the multiple reflow process can directly impact the interconnection reliability. So therefore, addressing how to enhance the reliability of the macro interconnection between the chips and inside the packages has become a major issues. And we propose a method for the nano-tuned copper pillar interconnects. And we develop a new zinc-doped desulfurization process during the nano-tuned copper plating process. So by applying the heat treatment to reduce the stress during the copper plating, it was found that after the copper plating process followed by 100 hours of heat treatment, and which can significantly reduce the stress levels, inhibit the formation of the conductor voids and cracks, thereby enhance the reliability of the interconnections. So here shows the heat-treated nano-twins copper pillar. And there is another very important phenomenon, like if we reflow the nano-tuned copper pillar, and the grain orientation transition will occur. And so we want to use this phenomenon to control the property of the micro interconnection. If we can get the preferentially oriented intermetallic inside the copper pillar, and the strength will increase, and then we can also control the growth rate of the brittle intermetallics. So we use this idea. We control the grain orientation of the intermetallics by the electric field to improve the bonding strength and the reliability. So we developed the low temperature rapid bonding method and achieve the interconnection in a very short time, which are about 180 milliseconds. And the directional control of the intermetallic also achieved. And we can see that the grain orientation grain along the 100 direction. So the microstructure of the copper pillar joint is very special, which can also enhance the joint strength. We can see that the directional growth intermetallic can enhance the resistance to electromagnetation, and compared to the traditional tin-based solder joint, the strength is increased about 2.3 times. And the first example is about the copper pillar interconnection between the chips. There are many the chip interconnection for the high power devices, for example, used in AI IoT, and the bump is only about 1 microns. So at this time, the bumpless hybrid bonding technologies enables ultra-fine pitch interconnection between chips. However, the direct bonding principle of the copper-copper path and the silicon oxides bonding at low temperature is incompatible, requiring the urgent development of the low temperature hybrid bonding technology. So we developed the method for plasma activation method. So we use the plasma to activate the silicon oxide wafer, and then we use the plasma to improve the surface energy, and then the copper surface oxidation occurred, and we can bond the copper and the silicon oxide together. And we also propose the copper and the silicon oxide surface hydroxylation strategy, overcoming the incompatibility between copper and silicon oxide bonding principles, and achieve the hybrid bonding at a low temperature, about 200 Celsius degree. And the binary synergistic plasma activation method is also proposed in our team to achieve bonding between the silicon dioxide and sapphire wafers, enabling the fabrication of ultra-sensitive mid-infrared spectroscopic detection devices. So we achieve the very high solution of the response of the spectrum to the number of the solution molecules. And based on the above interconnection technology, for example, copper pillar and hybrid bonding, so we applied this technology to fabricate the three-dimensional macrosystem packages. And here shows the 100 microns copper pillars. We fabricate this successfully, which greatly enhance the integration and the reliability of the macrosystem packages. So about two contents is about the macro interconnection, and then we also investigate the nanoscale interconnection technologies in the field of the flexible electronics. So we all know that flexible electronics will lead the new generation of the technological revolution. And there is a very important component named flexible transparent electrodes, and inside the flexible electronic devices. And the mostly commonly used material of the flexible transparent electrodes are ITO, and however, the ITO is brittle and which cannot endure the bonding and cyclic test. So the nanowires, the metal nanowires is very good alternatives to the ITO. So we can we think we can use our nano joining method to fabricate some nanowire network with a good conductivity and reliability. And the challenges is about the transparency and conductivity and bonding resistance and reliability. We developed some nanoscale interconnection technologies, such as light irradiation nano joining method, electrodeposition joining, and self-reduced nano sorting method. We used the laser, ultra-fast laser, and the electric field, and the sorting method fabricated the nanowire network very successfully and applied in the flexible electronic device. And also, I will choose two study examples. Firstly, we use the nano joining by the electrodeposition method. So We found that for the flexible transparent electrode of metal nanowires, we not only have the need for conductivity, but also have the requirement for stability. So whether silver or copper, which are very fragile, often require a protective layer on the surface to improve the stability. So we wondered whether we could realize joining and protection between nanowires at the same time. We achieved this goal by electrodeposition. So in the process of the electrodeposition, the nanowire can be connected while thickening, which improves the photoelectric performance of these electrodes. Furthermore, we prepared copper-gold alloy electrodes under the synergistic effect of the electrodeposition and the displacement reaction. The introduction of the gold element successfully improved the electrochemical performance of the electrode. And we electrodeposited polyethylene and tungsten oxide on the electrode surface as anode and cathode color-changing materials, respectively, to prepare a seismic electrochromic energy storage during functional devices. So we can see that for the copper gold alloy nanowire electrode, during the electrodeposition, the nanowire was connected closely. And we also characterize the performance of our electrochromic devices. The light transmittance of the device shows periodic changes under the periodic voltage according to the conduction. And the color change efficiency of the device can reach about 153. We also compared with it with the literature result. We have also achieved the same performance as some rigid devices. The device also maintained certain stability in the process of cyclic bonding and color change. And based on the research result, we fabricated the electrochromic supercapacitor, use composite materials. We use the silver nanowire and cobalt hydroxide and P-dot PSS. So with this material, the color efficiency and cyclic stability was improved. And based on the research above, we fabricated the all-in-one self-regulating ECD based on silver and the copper nanowire flexible electrode. And because the time limit, I will introduce this method briefly. So we also developed a method named self-reduced nanosorting. So with this method, we can join the nanowire together to make the rigid silver nanowire network. And then we coat the titanium oxide on the surface of the silver nanowire network. And then we use these electrodes to fabricate the OLED. And here shows some performance of the OLED. Based on the electrodeposition and the self-reduced sorting method, we developed the EHD printed method by self-reduced sorting. And that means by the electrohydrodynamic dynamic printing principle and combined self-reduced sorting, so we can print the silver nanowires. At the same time, the silver nanowire was connected together. And oh, sorry. Okay. I don't know why my slide was jump. Based on the EHE printed flexible electrode by self-reduced sorting method, we fabricated the flexible zinc-ion battery based on some composite materials. And the system was the zinc-ion battery was integrated. And the system was controlled using a competitive touchpad, which was set to snake routing and covered with PI tape and improve its sensitivity. And then, based on the good flexibility and the conductivity of the bismuth 2 and the tellurium, this composite material, a variable and flexible integrated system, including a series zinc-ion batteries, a touch controller, and a light LED was fabricated. So 2 flexible ZIBs in series were printed to supply enough voltage to power the LED. After varying the flexible device, a process of the thumb and the forefinger can activate the touch switch and illuminate the LED. And here shows some publications in the field of the flexible electronics. And finally, I come to the end. And thanks again for the invitation of Professor Alice Zhang, and Happy International Women's Day. And here shows the cake our PhD student. A lovely girl gave me this cake and some beautiful flowers. Our student gave me today, and which shows our as a professor, I think we are very happy today. And also, I came from Harbin, and Harbin is a very cold city, named the Ice City and the Music City. And this winter, Harbin is very famous. So thanks again, and welcome to Harbin later. And the beautiful scenery about ice sculpture and the snow sculpture. And it is very, I think it is worth to come to our city. So here some the acknowledgement. Thanks for the supporting from NSFC and some collaborative work with UCLA and IREC and University of Waterloo. So thank you again. Thank you for your kind attention.
Thank you very much, Yanhong. That's a lovely talk, and also the beautiful pictures of the flowers, cakes, and also the nice view of Harbin. So what we will do is now we'll introduce our second speaker, and then we'll invite Yanhong again to the stage for a panel discussion. So now let me introduce our second speaker. Let me bring my stuff. Okay, our second speaker is Veronica Augustyn from North Carolina State University, and she is the Jake and Jennifer Cook's Distinguished Scholar in Material Science and Engineering, University Faculty Scholar, and Associate Professor at North Carolina State University. Veronica also served as Associate Editor of the Journal of Materials Chemistry A and Materials Advances. Her research focuses on the design, synthesis, and the mechanistic understanding of materials for electrochemical, energy, and environmental technologies. She also leads an award-winning international project at North Carolina State, Bridge, which develops renewable energy research and education collaborations between universities in Africa and the US. her research and her group also being recognized with a number of awards, and in particular, she has also received the George H. Bless's Advising Award for her mentorship of undergraduate students. So Veronica, please, the stage is yours.
Okay, hello everybody. It's really my honor to be here to share with you our research, and thank you for the invitation to be with other distinguished female scientists today. It's a wonderful day to celebrate women scientists around the world, and I'm very honored to be part of the group today. So today I will share with you research from my group, where we've been very much interested in harnessing proton-coupled electrochemical reactions in metal oxides for energy storage and conversion applications. So a little bit about my research group and where we come from. Our focus area is materials for energy and environmental applications, with particularly those operating in electrochemical systems. And our core expertise in terms of how we accomplish this is through performing material synthesis, electrochemistry, and as you will see in our presentation, we use a lot of in situ and operando characterization tools to help us understand mechanisms. These are some of our recent research topics, things that we are interested in my group. Today, I'm going to touch upon just a couple of them, the behavior of protons and metal oxides and aqueous electrochemistry. And so that you can see where we come from, Raleigh is a city in the state of North Carolina in the United States, and North Carolina State University. This is one of our campuses called the Centennial Campus. Our lab is located just about here on the top floor of this building called Engineering Building 1. And this is what we call our Centennial Campus, which is where the main most of the engineering buildings at NC State University are located. And if you're more interested to hear more about our university and about our material science program, I encourage you to check out our website, especially for those of you that are considering graduate studies. We're a really beautiful location, and we have many different kinds of materials research going on in our department and at the university with fantastic materials characterization tools. So we welcome you to come visit us and also check it out. And I also want to acknowledge the collaborative effort that's involved in carrying out our research, particularly from the graduate students in our group. In today's presentation, I'll be showcasing a lot of the PhD work from Mike Spencer, who graduated from our group last summer and now is a postdoctoral fellow at Boston College, and Noah Holzapfel, who's a current postdoctoral fellow in our group, as well as some of our other recent alums. And this research is supported through the Department of Energy, through the Early Career Program for our work on hydrogen evolution reaction catalysis, and through the National Science Foundation for our work on the proton insertion side. Okay, so I know we have a diversity of research topics represented here today, and I want to give some orientation about the landscape of electrochemical devices and where my research group does a lot of its work. So electrochemical devices, whether we're talking about batteries, supercapacitors, or energy conversion systems like electrolyzers and fuel cells, they have this very large range of length scales that you can operate on, that you can do research on, right? So we can start from the systems level, thinking about the actual final devices that would come into your electric vehicle, for example. And you can also think about things at the cell level, right? Which is about how do you assemble the three main components, electrodes, electrolytes, into an electrochemical device. And then we start to get into the smaller length scales. Well, a lot of material scientists and chemists and solid state materials chemists, that's where we like to play, which is at the electrode level, at the material level, where we start to draw pictures of the crystal structures with the atomic positions, and that the electrochemical interface, which is where in all electrochemical devices, we say the action really occurs, the interface between our electrode material, our electronically conducting phase, and the electrolyte or the ionically conducting phase. And my research group focuses predominantly at this length scale of cell level and lower. And so what you'll see in my presentation is things that look like this, where we're thinking about the crystallographic arrangement of atoms inside the material and how do those change, for example, when they're undergoing an electrochemical reaction. Or how does this electrode interface with an electrolyte? How does a surface reaction, like the hydrogen evolution reaction, happen on the surface of this electrode material? The wonderful thing about this field is that there's really room for so many different viewpoints and areas of expertise. It's an incredibly interdisciplinary topic. So we need the scientists, we need the engineers, we also need all the folks beyond that. You know, we need the economists and all that. So it's an exciting place to do research, and especially for folks that are in the audience thinking about what areas to get into. I think electrochemistry in an increasingly electrified world is a wonderful field to be in. Another thing that you'll see in my presentation, and something that my research group has a particular interest in, is in aqueous electrochemical energy storage and conversion devices. So when we say aqueous here, we're defining the device on the kind of electrolyte that's present. And there's something unique about using water-based electrolyte systems. It leads to a number of benefits from a technological side, such as low cost, sustainability, safety, and scalability. And this last point is particularly important when we think about the need for grid scale battery storage. So battery storage for very large scale applications. This is the current installed grid scale battery storage. And then the red is what is predicted, what would be necessary to achieve what's called the net zero scenario from the International Energy Agency, where net zero means for global energy related CO2 emissions. So there's a big question right now about how do we go from here to here. And while that's an open question and there's many different ideas and opinions out there, I think from a fundamental science standpoint, it necessitates or it makes interesting aqueous energy storage devices. And then where do transition metal oxides come into play? When we're talking about aqueous electrolytes, transition metal oxides can provide scalability. They can also be very stable in aqueous systems. And importantly, they can have the necessary redox activity for aqueous processes. And when you're talking about transition metal oxides operating in aqueous environments across basically the entire pH range, those reactions will involve proton-coupled electron transfer, or PCET reactions, which is an even bigger landscape of chemical reactions that occur between protons, electrons, and our material of interest. So kind of, again, taking a bigger picture before we dive into some specific results, this is what these aqueous electrochemical energy storage and conversion devices look like. So there are aqueous batteries that would operate by having, for example, zinc electrodeposition and electrostripping on one side. And we saw an example of that in the previous presentation with the flexible zinc batteries. That was really nice. And then the cathode could be something that is a metal oxide undergoing a proton-coupled electron transfer reaction, maybe proton insertion into the solid state structure. Electrolyzers and fuel cells operating in aqueous electrolytes invariably utilize proton-coupled electron transfer reactions. Those are your hydrogen evolution, oxygen evolution, hydrogen reduction, oxygen reduction reactions. So again, what's special about protons for aqueous energy storage and conversion? These kinds of reactions will abound in aqueous electrolytes. In transition metal oxides, we can identify 4 different kinds of mechanisms that can take place. We can have protons adsorbing or inserting into the solid state structure, and I'll talk about that in much of my presentation today. We can also have proton-coupled electrolysis or formation of water at the surfaces of these materials. So these surfaces of metal oxides are serving as like catalytic sites for the subsequent reaction of molecules in water, in the water-based electrolyte. You can also have proton-coupled electrodeposition, or in this case, what's illustrated in here is stripping of the oxide. So where the proton will come in, and instead of inserting and remaining in the solid state structure, it actually drives the dissolution of the transition metal into the electrolyte. And finally, in some systems, you can even have proton-coupled electrolysis of the oxide itself. So if the material is something like this hydrogen titanate, H2Ti3O7, we hypothesize that we can actually reduce these hydrogens and form hydrogen gas just from the bulk of the material itself. And so there's many important considerations when studying these kinds of reactions. The factors like the pH and pKa, the concentration of hydronium ions, the tendency for that acid to dissociate, bulk versus interface, and electrode versus electrolyte are incredibly important. And because we have this diversity of different reaction mechanisms, it's also important to keep in mind that not just one kind of proton-coupled process may be happening. So when we think about metal oxides for energy storage and conversion reactions in aqueous electrolytes, the starting point is really to understand something about their stability, and that comes from the potential pH diagrams or the Poor-Bay diagrams. And that will readily help to identify metal oxides that we would expect to remain as stable solids at our pH of interest. So here I've just pulled out the potential pH diagrams for manganese, tungsten, and titanium. So these are all the essentially phase diagrams between water and the transition metal. And for something like manganese, which is a very interesting transition metal utilized in alkaline batteries, so alkaline aqueous electrolyte batteries working at high pH over here, very abundant, a lot of benefits there. If we start to think about shifting the pH to lower pHs, we find that this very large phase field exists where manganese will essentially be soluble manganese 2+. So if you're looking for a solid state material that can undergo proton insertion reactions, manganese is going to be very, very difficult to stabilize from a thermodynamic standpoint. And then I've identified on here these diagonal lines indicate proton-coupled electron transfer reactions, whereas the vertical lines are proton transfer reactions and the horizontal lines are electron transfer reactions. So this is a very useful starting point. On the other hand, you can have metals like tungsten and titanium, where in acidic conditions, you will actually find that they will have a stable oxide that's formed. And tungsten oxide in particular is a very, very stable oxide in acidic conditions. And that's one that my group has done a lot of work on, and I'll show you today. And it's because we want to avoid the dissolution of the tungsten into the electrolyte. We want to maintain the solid state structure. And so what I'll share with you today is a couple stories. I realize I'm probably running a little short on time already from our group on these tungsten oxides and how they undergo proton-coupled electrochemical reactions. The first will be on understanding the structural dynamics of these materials during proton insertion. And then the second story, if we can get to it, will be the interplay of this proton insertion process with a hydrogen evolution reaction that would happen on the surface of this material. So electrochemical ion insertion is an ion-coupled electron transfer reaction. And what that means is that you have what's called a double injection of an ion and an electron into your host material. So in an electrochemical system, we have an ion conductive phase, that's our electrolyte. That's where the ions are present. And in the case of aqueous electrolytes, they are hydrated. They must come to the surface of our electrode materials. And this is kind of a very zoomed in perspective where we say this is the crystallographic structure of the material. The electrodes themselves are these composites containing particles of our active material and other components to keep everything together. But if we apply the necessary potential between this electrode and a counter electrode, we can drive electrons into the electrode, and to compensate for that charge, an ion from the electrolyte will be inserted into the structure. And if we're in the correct pH for our particular material, that ion that's compensating could be a proton. And that's what we call this proton insertion coupled electron transfer. It could also be other kinds of cations. In the case of tungsten, you could have lithium, sodium, even magnesium. Importantly, to maintain the structural stability, the number of electrons that's transferred is less than 1. The interesting thing about this process is that besides the energy storage or the charge storage that comes from this ion and electron insertion, you also will have a change in the host material. You can have things like first order phase transitions, electronic changes in the conductivity, optical changes, and mechanical changes. And all of these we can also use as signals or as probes to probe the charge storage mechanisms. And so one of the things that we're interested in when I first started my research group is to compare proton insertion into 3 different kinds of crystalline tungsten oxides. Ones that were layered structures that also contained water molecules, and the anhydrous structure that was a 3-dimensionally interconnected material. And so, like I said, they all can undergo this kind of insertion process that's coupled to an electron transfer in an electrochemical environment. And we had several hypotheses about why structural water could influence proton insertion, perhaps lowering the activation energy barriers for desolvation, or even leading to something like Rhodes transport inside of the structure of the material. So we had some hypotheses about what could happen. So in order to dive deeply into what was actually happening in these materials, we performed operando X-ray diffraction. So we coupled electrochemistry with X-ray diffraction using synchrotron X-rays. And what we found was we were able to track the structural dynamics during proton insertion into those 3 tungsten oxide phases, the anhydrous one and then the 2 hydrated ones. And what we observed from these operando X-ray studies is that in the case of the material that had no water, there were 2 reversible phase transformations where the material was going towards a higher symmetry crystallographic structure induced by the proton insertion. So these phase transitions corresponded to peaks in the cyclic voltammograms. And they're illustrated here and then also shown here. So we would see merging of peaks towards higher, indicating higher symmetry phases, and this process was reversible. The interesting thing was that in our hydrated phases, the structural dynamics were less significant. For example, in the monohydrate phase, this layered structure, we saw that peaks would shift and merge, but there was no phase transformation upon proton insertion. So the structural changes were very, very smooth. In the case of the dihydrate material, we also saw that there was this tendency to go towards a higher symmetry crystallographic structure, indicated by changes in these peaks here, or as shown here, but then the phase ultimately reverted back to a lower symmetry at the highest state of charge. Importantly, in the case of the dihydrate material, the interlayer spacing was completely immobile, indicating that those water layers were not very dynamic in terms of the charge compensation mechanism. So here's some more details about how we actually track all of these structural dynamics during the proton insertion, the phase transformations happening in our anhydrous material, which is the more dense structure, and then the more smooth kind of solid solution processes happening in the case of our hydrated layered materials. So the implications of that for aqueous energy storage is that the proton insertion was much, much faster in the hydrated tungsten oxide phases. So this is a result where we were doing cyclic voltammetry on thin films of our metal oxides, going to very, very, very fast scan rates so that each cycle took just half a second. And you can see how the hydrated materials, same mass loading, same thickness, we're just performing so much more reversibly at this high rate than the material that did not contain water. And I'll go through this a little bit to just emphasize the point, is that these electrochemical kinetics are strongly tied to the deformation or the structural changes in the material, because the electrochemical redox, that electron process itself, not just the ion that's coupled to it, which in our case is a proton and actually doesn't take up much space, but the electron transfer process requires a change in bond length. So if you have a solid state material like a transition metal oxide, you will have volume changes or structural changes that take place to accommodate the electron transfer and the proton insertion. And to probe some of these kinetics, we utilized another operando technique. This is operando atomic force microscopy dilatometry, something that we performed together with Nina Balke, who's now an associate professor in my department at North Carolina State University, and Wanyu Tsai, who is now an assistant professor at University de Lille in France. And we use this operando technique to basically take an AFM tip and land it on the surface of our electrode and track the deformation in the height of our electrode as we're doing our electrochemical cycling, as we're putting protons and electrons into and out of the material. And what we find is that in agreement with the structural transitions that were showing these phase transformations happening when there was no water, that this more open structure that would contain water that had a layered structure had less deformation overall during ion insertion with less hysteresis. So the mechanics was really tracking, the electrode deformation, I should say, was really tracking with our electrochemical current measurement. So this measurement, this deformation measurement, is coming from a nanoscale atomic force microscopy tip landing on the surface of the electrode, whereas the electrochemical current that we're measuring would come from all the particles on the electrode. And what's really neat is that we could actually correlate this global electrochemical current that's shown in the solid line here with the very local deformation measurement that's coming from a single point on the electrode. And what we did here is we simply took the derivative of the deformation, the derivative with respect to time of the deformation from the previous slide, to map out how closely those two processes are linked. And since this deformation measurement is a local measurement, we can also scan it across the surface. So these maps are representing spatial dimensions along X and Y with the deformation rate and the color indicating the degree of that, or the intensity of that deformation in different regions. And we can see when there was water present in the structure, we had kind of more homogeneous distribution of that. And then when water was removed from the structure, it was much more heterogeneous. So we have a number of papers talking just about this technique itself for measuring local deformation of ion insertion electrodes. Okay, and so then we performed more operando X-ray diffraction to indeed kind of corroborate our understanding that these materials that contained water were just much faster at accommodating protons and electrons than the anhydrous tungsten oxide. So our conclusion was that it wasn't because we were observing a Grotius type mechanism or lower activation barriers for desolvation of protons that we observed this fast kinetic behavior in the hydrous material. Rather, it was the kinetics of the structural transitions necessary to accommodate the proton and electron that were leading to these significant changes between the three different tungsten oxides. And what I'd like to finish up for my presentation today is some of our latest work, where we started to ask the question of how this proton insertion process would interplay with the hydrogen evolution reactions. So I showed you before that protons in aqueous environments, there are many kinds of reactions that can take place that involve proton-coupled electron transfer. So we talked about one where protons are inserting into the bulk of our material along with an electron. So that's proton insertion coupled electron transfer. Another possibility, assuming that our solid state host remains intact and doesn't start to dissolve or be electrolyzed, is that those protons can come in and they can combine with electrons and evolve hydrogen gas from the surface of the material. That's what we call hydrogen evolution reaction. So we were interested in probing the interplay of those two processes, protons inserting into the bulk with electrons coming in, and protons reacting at the surface to form hydrogen gas. And this question is motivated by the question of, is the hydrogen evolution reaction, is it good or is it bad? From the standpoint of some energy conversion devices like electrolyzers, you actually want to encourage this process. You want to make hydrogen evolution very favorable. That's the energy dense fuel that you hope to derive. On the other hand, for most other aqueous electrochemical reactions, including aqueous energy storage, this hydrogen evolution reaction limits the potential window of your anode materials. So that makes it a negative thing. So what it comes down to is that understanding in detail how the hydrogen evolution reaction proceeds on the surfaces of materials is important for furthering aqueous electrochemical storage devices. And so, as I mentioned, our interest into this was just coming to with the perspective that some materials, like the tungsten oxides, are going to allow protons to insert into the bulk, meaning that in the more classic electrochemical language, they are non-blocking electrodes for protons. And we can make some analogies to the field of metal electrodes, which has received much more attention on the fundamental side. So you can have metals like gold that are blocking towards protons and the reactions are only happening on the surface. Or you can have a metal like palladium, which is very interesting because it can form a palladium hydride. That means that the protons and electrons can find themselves inside the bulk of the material and transform the material as more and more hydrogens are essentially stored inside of the material. That's why palladium has been considered as a hydrogen storage material. We have similar situations that can take place in metal oxides, and the proton insertion is very favorable in tungsten oxides. And so the question is then, how does it affect the hydrogen evolution reaction? So one thing that we did early on is we said, well, what happens if we turn the proton insertion off? And we can do that by basically modifying the structure of the material. We can intercalate into the interlayer organic pillar molecules, such as alkylamines. Well, they're actually alkylammoniums when they're in the interlayer. This is how we do it. It's a dissolution followed by reprecipitation process of the initial oxide in octylamines and heptanes. We see these microstructure changes that are happening as we form a hybrid material, and then we can exchange those pillars back for water molecules. So this process is reversible afterwards. This is a little bit about the structure. So we did a lot of characterization. When those organic pillar molecules are present, we can prop open the interlayer spacing quite a bit, up to 2.6 nanometers. So really open up the interlayer spacing in terms of the distance. And then what happens is we can probe the accessibility of the interlayer, and we find that when those organic molecules are present, we essentially shut the proton insertion and all ion insertion processes off. So whether it's protons, lithium ions, or tetrabutyl ammonium cations, we basically inhibit ion insertion into the material when those pillar molecules are present. And what happens as a result is that the hydrogen evolution reaction, the overpotential for that process is significantly increased if we do not allow proton insertion to take place. So what that means is that we need to have that proton insertion process to activate the oxide towards the HER. And so in some of our latest work, I'm just going to go through this quickly, we've further analyzed and correlated this behavior to the structural changes that are happening in the material, and find that there are, to kind of summarize, 3 possibilities for what is going on inside these materials. First, we know the proton insertion is modulating the electronic conductivity of these materials. The electron transfer basically renders the material a metallic conductor, and that's very important. The second is, and this is a hypothesis from our collaborators at University of Pittsburgh, that at very high states of proton insertion, you can be transforming the surface catalytic site from a hydroxide to a hydride, which is very interesting. And the third thing, which is something that we propose based on our work, is that there's actually the possibility of the involvement in the hydrogen evolution reaction in not only those protons that are available at the surface, but the protons that are inserted into the bulk of the material. And so I will come back here to my final slide and thank you all for the opportunity and look forward to the discussion. Thank you.
Well, thank you very much, Veronica, for such a very informative and thorough sort of investigation. So now I would like to invite our panelists to the stage. So Yanhong and Veronica, and I'd also noticed that next two speakers, Lingyan and Xiuyun, also perhaps here. If you are on Zoom, please do join us. And of course, Alice join us all together so that we can have about half an hour discussion, and then we'll bring the two speakers again for their talk. So yeah, Yanhong, your
Yanhong is
I'm here. I'm here, but I don't know what.
Your camera is not working.
Camera's not displaying.
Yeah,
It's okay. You can try again. First away,
I will close it and open it again.
Yeah, so I can see, yeah, all good now.
Yeah.
So is that the Lingyan is here too?
Lingyan very early should be online.
Oh, she's here, great. And excellent. So we also have Xiuyun here. That's right. So we got the whole panel here. Great. All right. So well, I probably will give opportunity to our panelists first to ask question to our speakers, Yanhong and Veronica. I'm not sure whether
maybe I go the first.
Please go ahead.
Always. So actually the beautiful talks, online they say that beautiful talks from beautiful ladies. Yeah. First I will deliver this message. We have about 15,000 iCANX, but today we also broadcast on another big platform is ScienceNet, so have more than should be now 40K audience already heard this beautiful talk. Congratulations. Yeah. Maybe I go first to the question part, Lan. Okay.
Yes,
yeah.
please.
So Yanhong, yeah, I noticed that you did very details all these works for the fabrications, semiconductor fabrication and all these things. So you graduated actually was from the department very traditional, for mechanics.
Yeah, very
right?
traditional. Actually, my major is very special. Welding.
Welding, yeah.
Yeah.
So
and then,
can you tell us a little bit again about experience, why you stick with all these tough things?
In Harbin Institute of Technology, welding is very famous, and I think it's the top one in China, and with different energy. For example, the aerospace, and for the big specimen as the aerospace, and for the small one, for the chip in the integrated chip. So use welding and joining can fabricate. So it's a multidisciplinary with many subjects. For example, materials fabricating, nanomaterials, electronics and mechanics, physical and chemical.
Okay, so you have the best research team, right? Yeah, so the people working together all in the top. But I really couldn't link this with such a beautiful lady, Nobody like, very kind of, so forgot about it. Just kidding, yeah. Well, I have this question for you. So maybe I go for Veronica, next question. So Veronica, so congratulations for very beautiful, work and all these things. I have a question for that. You have a chemistry background, right? You training in chemistry?
So I'm actually a material scientist in all of my background. Yeah. So I
Wow,
did all of my education in material science and engineering. But
oh,
when you do electrochemistry, I think increasingly, or maybe always, it's recognized it's an interfacial science, right? It's an interfacial science. So if you work with liquid electrolytes, you have to you have to learn something about non-solid state phases, and that's what makes it really fun. That's what makes
yeah.
research really fun.
Yeah. So from your talk, I think you're from a chemistry school or something. Yeah. It sounds like that. Okay,
Yeah,
great.
solid state chemistry, sure.
You're exactly right. I want, ask a question is because I'm delivering a message for the students, you learn something always usable, right? When you do research, you don't need to always worry about you have a background or not. Maybe you can learn a lot of new things, right? Yeah.
Yeah.
Not exactly, focus on that.
I
Okay.
think
Yeah.
that's the beauty of research is, when we train our students, we should ideally be training them in how to solve complex problems. That's the main thing, right? And to give them tools to solve the kinds of complex problems they would like to solve. Now, I probably couldn't jump into doing biology research like how some of our panelists will talk about today. That would be hard. But there are some things that are accessible, and it's one of the privileges of being a researcher is when you can follow what your interest is, right? That's a real privilege, I feel. So yes, I think that's really an exciting thing about being able to do research and following your interests. Yeah.
Super. Lovely.
Absolutely.
Yeah.
Yeah, I might just follow up with a very general question, Veronica, if I may. It's you talk about the battery technology is going to take over and rapidly progress in 2030 and 30. There will be a lot of things, a much higher sort of energy. So my question is that you talk also about this aqueous solution-based technology. So what that technology is sitting at the moment, and how you see that will be competing with other technology to achieve the goal in 2030.
Yeah, you bring up a really good question. And I'd say that there are many, many aspects to this, many aspects that are well beyond what we're doing in our lab. So for sure, what I'm talking about today, it's 2024, right? So 6 years from now, getting to that scale will require that for the time being, the technologies that are ready, that are scaled up, will be the ones that will be deployed first, right? Even if they're not the ones that maybe are the most ideal from a chemistry standpoint, if they are ready from a manufacturing standpoint, then those ones will go in first. And so, of course, that's going to be things like lithium ion. Those might be things like some flow batteries, and so on. My main point, I think, is that I think in a world where hopefully the cost of electricity will come down and the production of electricity involves less CO2 emissions, electrochemical technologies in general, electrochemical technologies for chemical manufacturing, electrochemical technologies for energy storage are going to become more and more dominant. So whether it's batteries, electrolyzers, or fuel cells, in my mind, the future is electrochemical.
But there's also you're talking about more, safety related issue, and
Yes.
so this have a big advantage.
Correct,
But
correct,
those
yeah.
solid state sort of battery, they're also, I would say they're also quite safe in terms of safety, right? So there's a lot of
Correct.
risk with that. So
So
what is the
yeah,
main?
so I think the main opportunity for solid state batteries is they're going to be coming in for things like portable electronics first. They're going to be coming in for, your cell phones, your laptops. These batteries will need some time to kind of get up to the kind of scale that would be necessary even for electric vehicles, right? Getting the kind of defect-free reproducibility and all that, again, on the manufacturing side. So I view them as like kind of premium systems, if you will. The solid state lithium metal or alkali metal batteries are the premium systems. Those are going to be our expensive systems. But then we also need some dirt cheap stuff.
So what is
And
really the price sort of difference here? I just don't have that sort of idea.
yeah. So there's, and when the larger the application, like when we say grid scale storage, actually there's a lot of nuance within that. What kind of grid application and so on. There's many different possibilities. And within that, you can target different chemistries. But like I mentioned at the beginning of my talk, I'm a scientist and materials engineer. There are many things that have to connect down the road. And a big one is manufacturing, right? The economy of scale. That's a big one. And that's difficult to predict. And I'm definitely not the person to maybe be the most authoritative on that either, right? I like to do operando characterization and studies.
Sure, no, that's fair enough. It's I can see research is really thorough and down to the fundamental science, which is extremely important to actually contribute to the overall improvement of the performance. So I think that's great stuff. Just a related question about your operando AFM. I saw like it's very small, of course, area you scan with the tungsten oxide. So I'm just wonder how uniform and representative that could be, like a big sort of large tungsten oxide film.
Right. So that's a really great question. So the operando technique actually touches upon something that I think electrochemists always want to know, which is, electrochemistry. When we do electrochemistry, it's from the signals coming from the entire electrode. But electrochemists, as people who are interested in interfaces, we actually really want to understand what's happening at a local atomic scale. So the AFM is something that can help us get to that smaller spatial resolution. And I showcased one one AFM technique that we've used, which is basically looking at the deformation of insertion electrodes and to absolutely get at that question of what is the heterogeneity of that process at the atomic scale or at the nanoscale. That's exactly the question we want to ask there. We have other tools to get at kind of larger length scale heterogeneity that are possible. But yeah, I think that increasingly in electrochemistry, we really want to ask the question of like, well, what is the heterogeneity of this electrode? How much could we, assume that everything is uniform? That makes it interesting and helps us design better electrodes.
Thank you very much. Back to Yanhong, I also have a very general question because I know everyone representing the general audience maybe here listen to your talk about chips, right?
Yeah.
And you're talking about this the bonding using the copper pillars.
Yeah.
And of course, we know that in the chips, you have high density of the different components. You probably have many of these little pillars. So what is the general method of making those pillars, and also what is the yield after you actually making so many in general?
Yeah. That's a good question. And the copper pillar inside the chips usually used in the advanced packaging. For example, chiplets and some microsystem and three-dimensional package. And the size of the copper pillar is only about 100 microns. And the method to fabricate the copper pillar is electroplating.
Electroplating, okay.
Yeah, electroplating. So nowadays, for the electroplating of the copper pillar, many researchers focus on this process. So we can fabricate about 30,000 microbond together. Yeah,
wow.
At those for the size of the 100 microns. Yeah.
That's very impressive. So normally they are pretty high yield sort of fabrication. You don't have any failure in theory because it's relatively actually large size from my point of view, 100 micron.
There are lots of failures. because
lots of failure.
reliability is very important during the electroplating, and also during the bonding process, and during the service of the electronic devices. They will the failure is very easy to occur at the interface of the copper pillar, at the interface of the copper pillar bonding. So it is very important to investigate the reliability.
Right. So I would just say, like in the industry, surely this problem's being when they have a production coming into this problem will be already addressed, or is actually quite common problem. So how does industry cope with that failure rate?
Firstly, after the fabrication of the copper pillar, there will be many methods to investigate the defects inside the copper pillar. Use the X-ray and some other advanced detection methods. And then, for example, in our research, we use some failure analysis to make the cross section and to investigate the failure mechanism. If the failure affected by the processing or by the electroplating process or by the mismatch of the CTE. So it's very important and it's very difficult actually.
Yes, I can imagine, but that's really, yeah, impressive, basically.
Yeah, thank you.
So we also, I've just noticed that Lingyan and Xiuyun just joined. Do you have any questions to ask our two speakers for the time being?
Yeah, I do listen to the two talks, and I got very good ideas from the two very brilliant scientists. So Veronica, I have a question actually. How did you do? I think you did a very good job in a cross talk between different disciplines, including mechanical materials, even other fields. So how are you doing in the United States about cross discipline connections and collaborations in terms of science?
Yeah, so that's a really great question. I would say we still, for the most part, everything that I talked about is still very much the domain of material scientists, right? The information aspects and things like that. But in general, yes, a lot of our projects are interdisciplinary with faculty from outside of my home university, actually. And I think a lot of that is just driven by the availability of funding that allows us to bring small teams of researchers together. So I would say my favorite kinds of projects are when I can have 3 to 5 faculty that we get to work together. It's a huge benefit for our students. It allows us to share resources with respect to instrumentation. I know when I was hearing Yanhong talk, I was thinking about, what are the kinds of instrumentation that's necessary or manufacturing tools that are necessary to even do this research. It's hard for one person or sometimes even one university to be able to have that. And so I'm grateful that we've had support from the National Science Foundation here in the US and the Department of Energy here in the US to help us build these small teams. And I hope that there's more opportunities like that. I also like bigger projects as well, particularly if we have a strong mission for this exact reason. We need different tools, from experiment to computation to help us bridge the gap. But I think students these days are really excited about those kinds of opportunities for the collaboration. At the same time, we do try to emphasize, or I try to emphasize, that we do need to have a strong foundation in our area of expertise, which is, solid state materials and electrochemistry.
I also thank you, Veronica and Yanhong, for your also very wonderful talks that you have given. And I have one question for both of you. I'm curious that during your particle engineering work, actually it's quite focused on physics and engineering. There are limited number of women scientists or women students in this field. So how do you envision in the future to mentor these young female students in your field? How to nurture them in different stage of development?
So I will talk briefly. I think resilience and grit is very important, and also insist in one thing. For example, for me, why I pursue my PhD because I cannot find a good job at that time. That's true. But after after I graduate, I found the research is very interesting. Our female scientist has many good character. For example, we can endure many things, and we have some good character, I think. Just insist in one thing, and finally you can find the beautiful things in during the research. Yeah. Insist, resilience, and grit, I think.
I think for me, I'm very grateful that within the electrochemistry and energy storage community, there have been some incredibly welcoming senior scientists, senior female scientists that when I was a graduate student, when I was a postdoc, kind of made things inclusive and would welcome me and others to the table. And I think that there's a huge role for people who have very high visibility as scientists and engineers to play in that, because it can help you when you don't feel particularly confident, you know, in maybe entering a space. So I'm very, very grateful to these people, and also knowing a little bit about, you know, what they were able to accomplish. If they had kids, for example, like I have 2 small children now, it can be a very difficult time when you feel like, you know, you have so many things that you're trying to accomplish but you only have 24 hours in a day. Like Yanhong was saying, the resilience. For me, it was very helpful to know that someone else was able to do it. And that gave me some confidence that maybe I could do the same and persevere when things are really, really challenging.
Yeah, persevere.
And so I think that like having a welcoming community, having a community that encourages junior students, junior faculty, junior scientists is so important for all of us to make it work.
Wow, I have to jump in. So Lan, I should promote iCANX again. You know, I think our iCANX is a really, really welcome, you know, platform for all the ladies. Yeah, every year we have this female scientist session, and every week we have a female scientist on the stage. But I tell you, I'm really proud of that. You see each flyers on iCANX. Every week we have to each flyers will have at least one female scientist, and in this group like Lan, me, you know, me, Xiuyun, we have 4, you know, female scientists as moderators. We have 4 men, you know, as moderators. So it's equally. So exactly like Veronica says that you have to see someone there, right? Yeah, you have to see in your field, in the stage, you are welcome. So this message is very important. So on iCANX, I think we try to deliver this message to the whole world. Lan, is that right?
Yes, I think that's very important, as you know, both Yanhong and Veronica's mentioned. I think a role model is important so that people see that if they can do it, we can also do it. That's a very important message. So people always sometimes say why whether it's important, you know, well, let's just focus, get things done, but to insist on some presence and agenda, balanced, you know, conference and like this platform, we really need to have that to make sure we make an effort so that you know, to inspire younger generation to keep doing and joining the STEM sort of areas is extremely important. And I'm really glad to also say that both Yanhong and Veronica is actually a great mentor, because Yanhong's got a beautiful flower and cake from her female friend. So they must really, really love you.
Look at my background.
I see it.
Yeah, those
Yeah.
are flowers.
Nice.
Yeah.
I haven't got any today. That's sad. That's good. I probably don't. I had a really late meeting with them today. It dragged too long. Anyway, Veronica, you also won this mentorship award, which is really impressive. So I would just say, what's your mentorship sort of philosophy or your sort of approach? And can you share a bit with us? Veronica, I was asking, yeah.
Oh,
sorry.
sure.
Yes,
So that's a really great question. I think that I have a general the general philosophy I have is that I really want to help my students get to where they would like to be, right? So if that means they would like to become a university professor, I try to help them with that. If they say they're more interested in industry, we try to think about, maybe if there's an internship that they could take during their graduate studies, or if there's a way that their PhD research could be a little bit more aligned with applied questions. So I think that's kind of the main thing. And then there's a lot of nuance because we're ultimately dealing with a lot of individual people, right? And so there's a lot of nuance in learning how to work well with somebody and work well with a student, and for them to work well with me, a lot of back and forth. So that's my general philosophy, is that I want this to be, I remember my graduate studies when I was at UCLA to be one of the most exciting and fun times of my life. I wasn't making very much money, but I made great friends and we had great fun doing research. And I would hope that when people leave my group, they feel like it was a worthwhile thing. That was like the most important part of my mentorship philosophy, is I want them to feel like it was a worthwhile investment. So yeah, other than that, in terms of how things are implemented, there's a lot of details about, having regular meetings and having plans for when to give presentations at conferences and working on how to write a manuscript and things like that. So, but yeah, I just want people to feel like this was a worthwhile part of their life. It's, 5 years typically is what a PhD takes. 2 years or so of a postdoctoral fellowship. And I think, I saw this quote recently or somewhere I saw it, like, time is the most expensive thing we have, right? Time is the most expensive thing. So,
yes. Oh, thank you.
So yeah, I try to be mindful of that.
Yep, that's really great. Yanhong,
Great.
and yeah,
Yeah.
here with us.
I have no question.
About your philosophy, how you actually, what is the important thing when you are mentoring your student? What do you want them?
Okay. Yeah, I know what you mean. Actually, I think I'm very lucky because in our department, our research field is about the chips. So our research group is very popular, and we have lots of the excellent students with a good character and higher grade. So they are talent, I think, and they usually I think I inspire them with the enthusiasm in the field of our field, because our in our research field there is a lack of a lot of people in our field in the electronic industry in China, so they can have a good job after the PhD or master graduation. So they love this research. I think I just inspire them for the enthusiasm of the love this research and love this field. And also, I think I gave them a lot of the inspiration on the life. I think I love life. I love life, and I love cooking, and I love pets, a lot of things. So I think my student was inspired by my life attitude.
That's great.
Yeah.
So it's not only you see
I
nice
tell you
work and
another
nice
story.
talent.
Yeah,
Yeah.
I tell you a backyard story for Yanhong. Yanhong also is a poet. No,
Yeah.
she write
Poet.
very beautiful poet. Yeah,
Oh.
so the student loves this very well. Yeah, so it make many beautiful things. You know, also it really like you know, artists sometimes. You know, a writer sometimes. Yeah,
Yeah, I
very
think,
good. Yeah.
yeah.
That's important to show students that as a scientist, you also have a life. That's important message as well for
Yes, yes.
Qualify life
young
and you know, very meaningful, you know, life. That's important.
Yeah, I think the student will think research is not boring, and
Exactly.
the research can give them a good job and a good life.
That's excellent. All right, I think that's what we have the time for this this session.
I have a last words before you say. I think you know, Yanhong got to the very good point. You know, for research, it's not you know only you can have a good job, you also can have a good life. I think this can be our Davos topic. You know, yeah, we will have you know all the speakers go to Davos summit and this July, so we can have a session like this. You know,
that's a good, important session. I would
you
say.
know,
Yeah.
beautiful job, beautiful life, beautiful research. You know, beautiful life.
Yeah, yeah.
Very good. It's nice
Beautiful
with
life,
that.
beautiful
Yeah,
research.
that's really good. So we were winding up this session, and I think thank you so much, Yanhong and Veronica, for joining us the first session. Now I will pass the stage to Alice. So she's going to host another next two talks, and thank you everyone. So see you next time.
See you.
Okay. Thank you, Lan, and great, you know, get everyone here. So interesting, and you know, oh, so sorry. Yeah, I opened the wrong file, you know. Yeah, I got you. Okay, yeah, please show us the next slides for Xiuyun.
Okay, you want? Okay, I'll
Find
show it. Okay, I'll share.
Okay, I found it. Yeah, great. So Lan, thank you. Yeah, so Xiuyun's page. Yeah.
Okay. Just give me a
Thank
sec.
you.
Yep.
Yeah. So, let me introduce our next speaker. You know, Xiuyun. Actually, I know Xiuyun. Last year, she joined us as a young scientist. You know, in the youth talks. You know, so I certainly, you know, loved Xiuyun because I love
I know.
still, you know,
Thank
beautiful
you.
work and beautiful everything. So Xiuyun was got her PhD from Cambridge, and he was a student president at that time, right? Yeah. So a very super leadership, you know. And after her PhD, she go to US for the postdoc. He did 2 postdocs, right? Yeah. So
That's right.
first it was in California, right? Am I right? In California. Then second,
You're
I go to
absolutely
Johns
right.
Hopkins. Yeah, so I
Yes.
go to Johns Hopkins. So did beautiful work and got great training, you know, that time, and then back to China during COVID-19. But it certainly set up her group and you know, got a lot of things. Now she already is a vice dean of the medical school in Tianjin University. So we're really proud of that. Xiuyun, stage is yours, please.
Oh, thank you so much, Alice. I'm really impressed by the very detailed introduction from Alice. So yeah, last year it was my great honor to join the panel, the iCANX talk invited by Alice as well. So this year it's really thank you so much. I listened to the 2 previous talk and I learned so much from the very brilliant 2 female scientists. And then it's such a great honor to attend today's talk. So I will share my PowerPoint and you can see it now, I guess. So first, happy Women's Day. Good morning and good evening, everyone. So it's like 9:30 in China, PM in China time. And so today my talk is like about like new development or new advances in brain disease diagnosis and treatments in neuro ICU, like neuro intensive care unit. Alice, should I like I need to stop at like a half past, like after 20 minutes or 30 minutes? Like I think it's
30
because
minutes.
30 minutes.
Yeah.
Okay, thank you.
Yeah.
So, like first, like I would like to introduce several very beautiful pictures of Tianjin University. As Alice just introduced, like we are based in the eastern part of China, and we have like a very beautiful 4 seasons here. So this is our campus. We have 2 campuses, and you are very welcome. To come to visit us, and I will definitely be your local guide. So today I would like to divide my talk into 4 parts, like background, research directions and progress, and also like future tendency. So my research actually a little bit different from like the previous 2 talks. It's about like health industry or healthcare field. So as we all know, brain disease is one of the most important disease. So globally, 1 in 6 people is suffering from brain disease, and actually the medical expenditure, the global medical expenditure actually is close to like 30% of the total human disease burden, and the brain disease accounts for around like 11% of all diseases. So in the past like 10 decades, around like 100 years, with the development of different brain monitor technologies, the intensive care, especially neuro-intensive care, become the most important department in the hospital, and which actually treats the most severe patients in the hospital, as you may know. So this is a very typical picture from ICU or from intensive care unit. You can see like we have like different kind of monitors. EEG for neuroactivity monitoring, beats for anesthetic level monitoring, intracranial pressure, Lycox, like cardiac monitoring is are used for brain and heart monitor. So our main job actually, like our research is like trying to use those kind of different technologies to get a better understanding of the patient and like give a better or a more precise clinical decision to the doctors to help them to treat the patients. So our main topic actually focus on these several brain disease, including traumatic brain injury, subarachnoid hemorrhage, hydrocephalus, and like cardiac bypass patients. So I'm sure like most of you may like be very familiar, may at least know this kind of disease already. So let's like talk one by one, but basically our research is like about like mechanism, diagnosis, precise monitoring, and personalized treatment for those kind of brain disease. So first, let's talk about hydrocephalus. Hydrocephalus, I think several people may have heard of that name. So like if you come to, like if you meet a patient or if you some of your friends have these problems, including urinary incontinence, mental problem, and also balance problem. And the doctors may ask you to go to have a brain imaging under MRI or under CT. And very probable, like you will have a big probability to get a big ventricle if you have these 3 like simple terms. And then, so what caused this like dilated ventricle? There are like several reasons. The most important or most popular 2 reasons is like a AD. You may know this disease, right? It's elder disease, like a neurodegenerative disease. The other main reason might be hydrocephalus. These 2 diseases are very different. Hydrocephalus is because like, you know, CSF is a fluid in our brain. So it's like a consistently being created from the ventricles, and then it will come out from the brain to our lumbar all the time. So if this block, the like circulation pathway is blocked, and then the CSF will accumulate inside the brain, and then which will cause dilated ventricle or zoom, like enlarged ventricle, which will cause those kind of symptoms or problems. And then for AD, it's because the neurodegeneration will give like more space to the ventricle, and while you create more CSF, and then the ventricle will be enlarged. So it's very different mechanism. Currently, like in the world, like globally, in every 500 people, we will have 2 to 3 hydrocephalus patients. It's also elder patient like disease, it's a degenerative disease as well. And then the incidence of misdiagnosis between hydrocephalus and AD is 1/3, which means like 1/3 of the shunt surgery, which is used for the treatment of hydrocephalus, will be misdiagnosed. And then the doctor open the skull of the patient and then put a shunt into the brain, and then they will find there is no effect of this surgery. So that is a very big problem, and that causes a big cost to the patients as well. So last one, the traditional method for the diagnosis of hydrocephalus needs like 2 to 3 days. You need to bring the patient to the hospital and to do a CSF release. We call it like say a CSF TT test. After the TT test, you need to put a patient in the hospital to stay for another 2 to 3 days to make a general decision whether he needs a shunt surgery or not. So this all increase the a burden of the clinical doctors and the bedside nurses. So we are thinking, or whether is there a faster, a more precise way to diagnose hydrocephalus. So that is like related to, I'm so sorry, this slide is in Chinese. So that is related to the CSF formation and CSF absorption. So the CSF is a fluid in the brain. So it is constantly created or secreted in the ventricles. And that is closely related to some tight junction proteins. And then for the CSF absorption, there are like 2 main pathways. One is like the CSF created here. Okay, this is like a called this name. So choroid plexus, okay, so it is created from choroid plexus and then goes through the 3rd ventricle, the 4th ventricle, and to the subarachnoid space, and then will be absorbed to the heart, to the lumbar. So this is the main pathway of the CSF circulation. Another pathway is the brain glymphatic system. So that is closely related with CSF absorption, which is driven mainly by the arterial pulsation. So this is like where our main research lies in. So first, for hydrocephalus, we don't have a fast and a quick decision, like a diagnostic tool to help the doctors to make decision. Second, they don't have a very objective way to do the decision. So we did some very general literature review. We found hydrocephalus is inherent, right? So some you will see some babies or some newborn babies, they will have very big ventricle, they will have very big brain. That is closely related to their genetic mutation. So then we found, okay, some very typical genes that is related to cilia movement, to hyperpermeability, to the nervous system neurodevelopment and neural growth, nerve system growth. Those kind of genes, if they are mutated, and then the baby will have a very high probability to get hydrocephalus after the birth. And then you can see this is the cilia movement, and you will find, okay, if the genetic genes are changed, and then the babies may have some problem with their ventricle. And also, if the baby grow to the later stage, for example, to the adolescent stage, you will find these genes are not only located expressed in the brain, they are also expressed in other very important organs like a kidney or heart or lungs. And then they may have a problem in those organs as well. So now we are trying to use our clinical data to validate our hypothesis. And then currently, we did some like genomics, proteomics, and metabolism analysis, and we found some very typical and specific protein biomarkers for the hydrocephalus identification. But those data like hadn't been published yet, so I didn't put them here, like fully put them here. But later, hopefully after published, and hopefully to share the results with all the audience. And then a second problem for hydrocephalus is currently in clinical side is about the hydrocephalus the diagnosis. So this is like a traditional way here, how we do the hydrocephalus clinical decision. Like the patient came here, we do a brain imaging, we do like a consciousness test, gait problem test, and then we do a lumbar puncture, put a very long needle into the lumbar space to release like 30 cc to 50 cc CSF, and then you gave another like a CRSR and also brain imaging test at like 12 hours, 24 hours, and 72 hours. And you see whether the simple terms like is improved. If yes, and then the patient may be diagnosed as a positive case, and then a shunt surgery may be followed after the decision. So what we did is like actually this work is like where I did like we did in Cambridge University, and now we are actually applying it into the Chinese hospitals. So what we are doing is like we do an inferior study. After the lumbar puncture, we connect the lumbar space with our monitor, and then we do a like infuse around like 5 to 10 cc CSF saline fluid into the lumbar space, and we use physical equations to simulate the circulation pathway of CSF and try to diagnose this patient. So if this patient is a hydrocephalus patient, you may say the CSF like a pathway, circulation pathway absorption resistance is very high because CSF cannot be absorbed easily. But if this is an AD case, it's not a hydrocephalus case, and then you will see the resistance of the CSF circulation is very low. It's like normal. So in this way, we can separate or like distinguish patient with hydrocephalus or with like AD or brain atrophy or with other like arterial blood pressure, arterial disease. So in this way, we will give a very like a precise diagnostic decision for the doctor. And then this is a very like a specific case. So this is in our like Huanhu Hospital. Is a brain center in Tianjin city. And then you see this patient. Like while she came here, she cannot move at all. She can only she was lying there. She cannot move her body. She cannot sit up. She cannot move. She cannot walk. And then we did this clinical report, and we found, okay, her resistance, CSF resistance is really high. And then we suggested the doctor to do a shunt surgery. After the shunt surgery, 2 days later, you can see she's walking freely. So currently we apply this technology into like around 300 patients already. And then besides that, we also use like brain computer interface. I don't know, have you heard whether you have heard of this name or not? Brain computer interface is recently gained big popularity and gained like high attention from the audience and the patients. So basically what this technology doing is like it actually collect our EEG data to try to read your mind, to know what you are thinking about, and then try to control a mechanical robots to do whatever you do. So it has like has been widely applied in rehabilitation field. So in this intensive care unit, what we are doing is like we design different stimulation model, like using like colorful pictures, use different auditory stimulation to stimulate the brain of the patient. You will see for AD patient, normal patient, and hydrocephalus patient, their brain response is very different. And in this way, we can find a very objective goal or marker to treat, to diagnose the patient, the patient. Here is the example. This is like a hydrocephalus positive case. You can see this is before TT test, and the brain network like connection is really small, very low. And then after the TT test, you will see after you release CSF from the brain, and you will see the brain connection is like increased so much by a large scale. So this is how we actually trying to apply the brain computer interface technology into the intensive care unit for the patient like diagnosis. So in this way, we develop a device demonstrated here in this picture. So we combine the brain-computer interface technology, combine the protein biomarker of the hydrocephalus, and combine the CSF circulation resistance parameter together, and we can actually decrease or shorten the diagnostic length from 3 days to 30 minutes. And to try to save that cost for the patient. Then after you do the decision or after you do the diagnostic, the next step is like treatment for the hydrocephalus patient, right? So current traditional way for the treatment of this kind of patient is like putting a shunt into the brain, like as shown here in this picture. And then you dilate, like direct this kind of CSF from this pathway into your lumbar, into your heart. And then in this way, this shunt will stay in the brain all the time, and it will cause a lot of problems. So we are thinking whether we can use some neuromodulations, non-invasive ways like electrical stimulations, ultrasound stimulations, try to treat and cure this kind of brain disease. So currently, we got a very good result from our animal model. We use mouse. We established the hydrocephalus model by inducing some like blockage to the artery of the brain, and then we do use like a non-invasive vagal nerve stimulation, trying to see whether this treatment can cure or treat this disease. And here are some like results. So you can see this is control ventricles. This is like a hydrocephalus rat ventricle, very big ventricles. And this is like the ventricle, rats treated with like a VNS, like a non-invasive vagal nerve stimulation. You can see the ventricles is like decreased so much. And also from the behavior test, we can see like the consciousness level, the movement level has been increased significantly by using this non-invasive stimulation. So hopefully next step, we are going to try, this is like the brain staining. You can see this is like a control brain, and this is hydrocephalus brain with like damaged ventricles, and this is like the hydrocephalus brain with like the VNS stimulation treatment. You can see it's very good and round shape of the perfect shape of the ventricle. So next step, hopefully we want to apply this technology into clinical trial and for the hydrocephalus patient treatment. And also, we are now actually using zebrafish to try to find or develop some new drug for this treatment and for this disease, because currently we don't have a very efficient drug to treat hydrocephalus. And now we find a structure, we call it like TH9. It has like a significant effect in treating those kind of hydrocephalus simple terms. So hopefully we can bring some like a non-invasive way, including the stimulation, electrical stimulation, including a drug. And here is, we call it a digital medicine. Like the first digital medicine who got like FDA's developed by Professor Gasly in UCSF, like University of California, San Francisco. So I stayed there like for 2 years, and I know his job very well. He's a great scientist. So what we are doing here is we are trying to use like paper folding to help those kind of old patients with hydrocephalus to regain the ability of the space determination. So you can see like we have very consistent improvement after the paper folding training for the older people, and hopefully this is a new discovery, and then hopefully we can like apply them to the new treatment of the hydrocephalus patients. You can see after the paper folding training, the brain network or brain connections has been significantly increased So that is like that shows actually great potential for the treatment of the hydrocephalus patient. Okay, so like next I would like to talk. I think I have like several minutes still, like maybe 7 minutes. Okay, so I will talk about like another research we are doing in intensive care unit is about personalized treatment. So the brain,
Xiuyun, you still have about 10 minutes, but you
10
need
minutes?
to move your chair up. Okay.
Okay. I'm trying to speak as fast as possible. Okay, so next, maybe I just introduce 2 topics today. So this topic is about personalized.
Xiuyun, get us, a little bit higher. Now you move out to the camera.
Here. Oh, this is better. I'm sorry.
Yeah, better.
I'm looking at another screen. Okay, so this is about another work we are doing in intensive care unit. It's about like the personalized treatment of the brain. So as we may know, the brain is really a small organ, but it's very important. It actually weighs only like 2% of our human body's weight. But actually it costs or consumes around 20 to 20% of our oxygen and nutrition. So it is an organ that needs consistent cerebral blood flow like supply. So how did they achieve this? There is a very important ability of the brain. It's the cerebral autocoagulation. And actually it's related to your artery of the brain. So if you have a good artery, then it can constrict or dilate very easily, and then it can keep your brain have a constant and stable blood supply, and then that means you have good cerebral autocoagulation. But in intensive care unit, as you know, they are all very severe patients, so their brain is very fragile. So how we treat those people's brain is a problem. How could we supply enough blood to the brain? Not too much, not too little, not too less. That is a problem. So what we are doing actually is like we are trying to use like different technology, monitoring technology, including arterial blood pressure monitoring, intracranial pressure monitoring, cerebral perfusion pressure monitoring, to calculate or to assess the arterial blood, the ability of the cerebral autocoagulation of the brain. And then we will see for the patient who died, they have very bad autocoagulation in ICU. And then next step, we are trying to use this ability to determine or to locate the best personalized arterial blood pressure to help the doctors make the final decision. So this is a case that you can say, well, the doctors come here and the patient real blood pressure is like around 80, and then like his brain actually need like the blood pressure of like 85. Then the doctor knows, oh, I need to increase his blood pressure to direct the doctor's clinical intervention. So we will see actually these kind of interventions or this kind of personalized treatment actually is really helpful in increasing the favorable outcome of the patient. This is like from like a data analysis from 500 TBI patients. And then we also applied this technology into the cardiac bypass patients. For cardiac bypass patients, 52% of the patients will have delirium after cardiac bypass surgery, and 30% of the patients will have acute kidney injury. So we are thinking about why the patients will have this problem. And one possible reason may be because of the, during the surgery, the patient uses all the bypass pump, and then how much blood pressure you set actually influence the blood perfusion to all the organs. So if you set the blood pressure too little, like too small, too low, and then you will not have enough supply to the organs, and then you will have delirium in the brain, you will have the acute kidney injury. So what we are doing is that we determine the lower limit of the autocoagulation for each patient. That means we determine the lowest arterial blood pressure level he can accept for each patient before the surgery. And then the doctor during the surgery, they will know how low they can come to treat this patient. So this is an example. This is like a paper we published in BGA. That is a very good journal. You will see the longer low blood pressure, the lower the blood pressure is, actually the higher probability the patient will get AKI or get like delirium. So in this way, if we give the indication to the doctors, actually, we will decrease the comorbidity of the patients after the after the cardiac bypass surgery. This work was done in Johns Hopkins, and currently we are doing it in the Tianjin Chest Hospital for around 1,000 patients. And then we also find this treatment is very good or very helpful to prevent the heart failure probability after the cardiac surgery. So I will quickly just go through several slides. Furthermore, we also doing some new treatment development for Parkinson's disease. As you may know, Parkinson's disease is also a neurodegenerative disease. So we found there is a very traditional Chinese medicine is called Arucus Sylvester Coastal Root, like Jiashenma. That the main component of this drug is actually ASE8. And then we think because it has neuroprotective effects, we want to find out how and why and whether this ASE8 is helpful or good for treating Parkinson's disease. So we use zebrafish and to do several experiments, and we found this ASE8 mainly protects dopaminergic neurons and preventing neuroinflammation in the zebrafish, and as shown in these pictures. I will not give details and because due to a limited time. And then we validated this component in the rat and the mouse model, and you will see this is MPTP induced Parkinson's disease, and this is like ASE treated group, and this is control group. You will see the ASE is really helpful for improving the brain function of the PD model. And then this is we have done some other job with the development of AI technology. We're also trying to apply this AI technology and AI toolbox for the clinicians. This is a work we collaborate with several Chinese hospitals. The doctors came to find us and told us they have problem in identifying the spike waves for epileptic patient or seizure patients. So we are trying to use a multitask transformer network. This is the AI model to help the doctors to identify the spike waveforms from the EEG signal for the epileptic patient to help the doctor make the final decision, where this epileptic happens, in which brain lobe. And then we can also identify the positive or negative spikes, and then to help the doctors make a better decision and save the time of doctors. Finally, we actually are trying to develop a new non-invasive monitoring technique for intracranial pressure monitor. As we may know, the brain is a very rigid box because of the skull, and then it is very difficult to monitor intracranial pressure non-invasively, but intracranial pressure is really important because if it's too high, you will have herniation, which will cause death. And then we are using the optical laser technology. We trying to non-invasively monitor the managing or meningeal absorption or absorbance or a dural absorbance to reflect the ICP intracranial pressure. This is invasive intracranial pressure. This is non-invasive absorbance, and you will see they have a very good linear relationship. Now we have finished the animal model, animal experiment part, and we are trying to develop it into a small device, and then we are trying to use it at the clinical side. So these are other techniques we are trying to develop. For example, this one is we are actually developing we developed a toolbox for the sepsis patient multi-organ failure prediction. So in ICU, sepsis has a mortality of 1/3. So one in every 3 sepsis patients will die. And the main reason is you will have multi-organ failure after inflammation. So you will have like a lung disease, lung failure, a liver failure, kidney failure, respiratory failure, heart failure, and then these people will die. So we are trying to use clinical tests or the data set and then try to predict the multi-organ failure earlier, at least like 3 days or 1 day early, and then to remind the doctors to do the right decision and to do the right clinical intervention. And then now we develop it into a APP, and then this is like how this works, and it will remind the doctor every day whether this patient will have like a heart disease or lung heart failure or lung failure, and then remind the doctor what is going to do, what he needs to do next. And then this is the last part. We are trying to also analyzing the sleeping pattern for the patient, for our humans. So we have like around 1 people's data, you can see like our sleeping pattern really differs at different age. And that is really closely related to our memory, to our brain function, to all our to the brain health. So we are trying to summarize this, and this is like currently under like a writing stage, and hopefully it can be published this year, and then to tell us what is happening during the age development in our sleep stage. And so basically, what we are doing is actually we are trying to find the new treatment for brain disease, find a new monitoring for the brain disease, and also try to find the basic mechanisms of the brain, how the brain disease happens. Currently, we are facing several problems in challenges in the intensive care unit. Like there is no criteria, for parameters that what we need to monitor, and then we don't collect a lot high frequency waveforms currently, especially in China, in Chinese intensive care unit, and also how we collaborate or connect the HER, like a hospital electronic record, clinical interventions, and high frequency signals together. That is also facing a big challenge. And then so I think in the future for the intensive care unit monitoring, there are several trends or tendency. One is continuous and precise. One is multimodality and non-invasive. Finally, it's like personalized and predictive. And hopefully through all these toolbox and also intelligent medicine techniques, we can actually help the doctors to lower the patient's cost and improve patient satisfaction. Most important things, we try to improve patient outcome. So thank you so much. I'm so sorry. I think I run out of the time. Thank you, Alice.
Great. Yeah, Xiuyun, as usual, wonderful talk and very productive. I think in the last 2 years, you really like sleepless, you know. Yeah, 24 hours
true.
working, got so many results. Okay, so we go to the discussion later. Okay.
Okay,
Yeah.
sure.
So
Thank
now
you.
we have Lingyan here. Actually, Lingyan was giving me very great feelings during your rising stars, you know, light rising stars. I think that time, you know, I listen on the talk every day, you know, for the rising stars. And when I saw Lingyan, I heard your talk, I said, oh my God, that's a star. Yeah. So Lingyan was associate professor, assistant professor in UCSD, and she developed really beautiful imaging technologies. So Lingyan win a lot of, you know, honors. I think also transfer technology, you know, to the real product. So Lingyan, without further ado, you know, please, the stage is yours. Yes.
Thank you so much, Alice. I appreciate your detailed, very detailed and great introduction. And I'm going to share my screen first.
Yeah, please.
If you can see my screen now.
Yes.
I changed a little bit about my title to Metabolic Nanoscopy. Nanoscopy, the nanoscale, nanometer scale scopy for study aging and diseases. I'm from UC San Diego, and it's my pleasure, and I'm so happy to share our recent study in the lab. So first question, I think the audience also will ask why we image biomolecular or cellular dynamics. It is very important for understanding the biological processes, including genetics and the metabolism. So we actually, from visualization of biochemical interactions in space and time, we can understand more about the complexity of life. It has very far-reaching implication for human health and also the progress of scientific research. So this is important technology that I'm going to introduce today. We have been involved in the HubbMap program, the Human Biomolecular Atlas program. This program is a global and open platform for us to map the healthy cells in the human body, different organs actually, including the guts organ. And it is a great reference for medical researchers and biologists to see how the healthy cell looks like in the human body and also the molecular composition. For example, protein, lipids, DNA, RNA, or carbohydrates, how these molecular spatial distribution and their 3D volumetric distribution inside these organ tissues. And our colleagues in the HubbMap program, they have generated many multiplex image to visualize different protein molecules. So these are a few examples that I display in various human organs. It's like a atlas from different gut tissues. However, these beautiful images are only for protein molecules because the imaging technology for lipids, that is the fat molecule in the body, are very limited. So the imaging technology for visualization of fat molecule, almost you cannot find those high resolution one. But along the human evolution, we can see that in our body, more and more fat deposits occur, not only because of the diet, but also due to the lifestyle change. These fat molecules is extremely important for our energy homeostasis. You can see from brain or muscle or other organs such as the liver, it's very important to understand how the fat molecule are metabolized in the body. As just mentioned that how was the metabolic imaging looks like in the hospital, we all learned about the PET and MRI. They provide the metabolic activity information. However, the spatial resolution is relatively low, so we cannot see cellular level. For biologists and medical researchers, they sometimes want to know the cellular machinery, that is even a subcellular organelle level metabolic dynamics. So at that moment, the optical imaging technologies are preferred, such as fluorescence microscopy, which is from electron outside of the nucleus. We are very familiar about fluorescence microscopy. And today I'm going to add another technology called Raman-based. It's about the motion between nucleus. And this is about chemical bond imaging. We can visualize chemical bond, and the vibrational modes of the chemical bond can be collected in certain signal. Then we can see the spatial distribution. And these are very high spatial resolution technology that we can see a single cell or even inside the cellular organelle, such as mitochondria or lysosome or lipid droplets. But as mentioned, the fluorescence microscopy is widely used not only because of the high spatial resolution, but also the commercially available fluorophore that we can target those molecular of interest. But for Raman, in contrast, it provides the chemical bond vibrational frequency information. In the lower right side, you can see different chemical bond vibrational frequency from different biomolecules. So in theory, we can simply pick one of the chemical bond vibrational frequency and do the image for that chemical bond, which map out the molecular spatial distribution. In reality, the spontaneous Raman microscopy has very low sensitivity, so it's really hard to do the video rate imaging. But we can see each molecule has its own Raman spectrum profile. If we look at these molecules Raman spectrum profile in our own library, we measure these 100% purified compounds one by one and establish these fingerprint signal. For example, you can see cholesterol, how the cholesterol looks like, how the sphingolipids looks like, how these omega-3, omega-6, they have their own Raman spectrum profile. It's like you have your own voice or sound wave. I have my own voice or sound wave. So each molecule have their own sound wave, and we can distinguish different molecules based on this Raman spectrum profile. So with this theoretical background, I think we can look at one example for sperm cell. If you look at the bovine sperm, we understand that the sperm head have DNA, and the sperm tail almost have no DNA, detectable DNA, no detectable DNA in the tail. So if we focus a laser beam, this is a light microscopy. If we focus the laser beam only on sperm head, we can collect a spectrum on the left side, which is in blue color on top, and we can see the DNA molecules signal. You can see peaks from 781 centimeter inverse, 1091 centimeter inverse. These are DNA signals. But if you move away the laser beam and focus only on the sperm tail, then you can collect another spectrum, which is on the left side, lower red color spectrum. You can see that DNA molecules signal are all gone. So that means if you want to image a DNA spatial distribution, you want to see where is DNA located, you can simply pick up these peaks such as 781 centimeter inverse or 1091 centimeter inverse for DNA image. So this technology is a chemical bond vibrational modes based technology. It can be integrated into fluorescence. For example, TPF here is 2 photon, 3 photon fluorescence. SHG here is second harmonic generation. SRS here is stimulated Raman scattering, which is the technology that we just mentioned. It's a Raman-based chemical bond vibrational imaging technology. 3 of these modalities can be integrated into a single microscopy in the lab. So how we can collect many different type of signal or molecular information at once. We simply put the sample or animal, you can either have cells or tissues or animals under the objective lens. Then we collect these different type of signal for analysis. So including the fluorescence or second harmonic generation or Raman signal, that it can be 2D or 3D, and the molecular information can be dissected like this. One example is if a patient is worried about their kidney. So some of the patients have a diabetic symptom, and they want to know if the kidney have any problem. So what we do is the medical doctor will help to do a needle biopsy, just insert a very little tiny tip of the needle and grab little tiny piece of tissue out of the patient. So the patient will just provide less than 1 millimeter of tissue, and then for us it's a lot of tissue already because the high spatial resolution. So we can see under the microscopy to collect the different modalities of a signal. So we can do the fluorescence microscopy for NADH and flavin to generate a redox ratio. That's the metabolic activity changes, especially for glycolysis or oxidative events in the cell or tissue. And the second harmonic generation allows us to collect those extracellular matrix, especially the collagen network. So you can see the yellow channel is about the collagen. The collagen is also very important for skin, for example. If we lose collagen, our skin will be wrinkled. So in the kidney, there are a lot of collagen as well. The collagen network can be changing under the diabetic symptom. So we can see how these collagen fibers density, curvature, or these orientation or disorganization can occur after the diabetic symptom. SRS imaging can provide us lipids, protein, or DNA, RNA, or other carbohydrates molecules signal as well. So we can merge different channels of molecular information together to generate a multiplex image like the right side. It looks like a peacock tail, but actually this is a molecular map. We map it from the patient biopsy tissue, And you can see the cyan color are those protein signals from glomeruli in the kidney. The glomeruli are very round or spherical shapes. And the green color are from second harmonic generation of the collagen molecule. The collagen network can be mapped out simultaneously in the same region of interest. And the magenta color, or you can see purple color, they are from the protein molecules signal in those vasculature system in the kidney. And the red color, they are lipids, which is the fat molecules signal from those kidney. Although we have many more channels of different molecules, but I just showcase this a few of them to let you know the flavor about multiple molecular information. And if we zoom in to see the details of those glomeruli or tubules or even the ducts, we can see even inside one single glomeruli, there are different types of cells. And these cells have different molecular composition. We can really visualize by the hyperspectral image from this Raman-based technology. So it's totally label-free. Label-free means you don't need to scan anything. It's all from the endogenous chemical bond information, and it can be 3D or 2D manner. So then we can do the 3D by scan from the top layer to the bottom layer. And if you reconstruct them into a volumetric image, we can see different types of molecular information. So these magenta color, you can see they are deposited outside of the glomeruli in the tubule side of the kidney. We can see that network very clearly, and we can see the change under the diabetic symptom. Inside the round shape, that's the glomeruli, we have observed many different types of cell. These are subtypes of cell inside those glomeruli to do their own job. And those green color on top, they are lipids accumulation. We can see the fat droplet accumulation under those diabetic symptoms. So it does change the molecular composition when some disease such as diabetes occur. We have observed extra amount of fat molecules in the tubule side first. So we can see that this can be layers by layers if we want to do quantification for different layers of the tissue in a multiplex way. So each layer have different types of molecule, and you can do from top layer to the bottom layer to map out those structural functional interaction. And these arterial or nerve or collecting ducts, how they interact with each other are all clearly mapped out in this multiplex image. And it can be also combined or integrated with spatial omics profiling with super resolution SRS imaging cell by cell on the same tissue. So that is really map out those single cell level omics and the metabolic activity, dynamics, and the function. They are structural functional interactions. We can see more than maybe 100 different type of molecules at one time. So the major challenges here, we just talked about label-free, right? All from the endogenous molecular information or endogenous chemical composition information. We are not very satisfied with only looking at that kind of signal, because we want to see more. What is more about the molecular specificity, how even the subtypes of fat molecules, such as cholesterol or omega-3 molecules inside a single cell, and inside the organelle, such as mitochondria, lysosome, or even the lipid droplets, those very little tiny cellular organelle level metabolic dynamics. And we also want to distinguish which molecules are newly synthesized and which molecules are pre-existing older molecules. And then we can map out the real metabolic dynamics. So I'm going to address these questions by the newly developed technology in our lab. The molecular specific, the concept of this specificity is similar to those mass spectrometry-based technology, because we know each molecule have their own Raman profile, that is these spectrum information. So we established the library by measure these 100% purified purify the compounds one by one, establish the library in the left side. You can see those spectrum from each molecule. Then we do the hyperspectral image on the tissue or cell or animal, or even human tissue. Then we can compare the reference spectrum from the standard in the library and with each pixel's spectrum, because each pixel have the spectral information with the reference matching with penalty. This is the algorithm that we designed to detect for each pixel. So that means each pixel we can see the similarity score with the reference spectrum. If there is a pixel that have similar spectrum with a single lipid molecule, that is a subtype of fat molecule, we can show these in red color on the right side. So these red color pixels are high content sphingolipids. The lower blue is triglycerides, another subtype of a fat molecule, and another green color is the cholesterol. So we can merge them. So this is totally label-free from the human brain sample. We can map out these molecular information without any staining, and it's quite convenient and efficient for us to visualize the molecular composition change and the aging or disease. So you can see how we can also merge these different colors detected with label-free technology. So the magenta color are from lipid droplets. The cyan color, they are from those lysosomes. So how we can detect the whole lysosome? This is a cellular organelle. We don't care about what's inside that kind of lysosome. We care about the final chemical composition. That final chemical composition will generate a reference spectrum. So with that reference spectrum, we can detect all pixels in the image that have similar chemical composition. Then you can map out those cellular organelle directly without any labeling. So that's the spectral information from each of these organelles in the tissue. So if we don't know what's going on or what kind of chemical composition in these tissues or cells, you can see from even mouse brain or human kidney or Drosophila brain or even a single cell that are doing mitosis. That is a cell that are dividing but not separated yet. At that moment, we can do the snapshot and map out those newly synthesized molecule. If we do the unsupervised clustering technology, we can see those pixels in the image can be groupized. That means for example, the red color on the lower right side, you can see the red color pixel. These are perhaps newly synthesized DNA molecule that you can map out directly, but other things can be validated by other technologies later. So for cellular organelle level information, we really want to see how we can generate super resolution, because the single cell is the unit of life, and we know how important a single cell or cellular machinery can be. Those mitochondria, lysosome, or lipid droplets, or other organelles or Golgi apparatus inside these, including ER membrane inside a single cell, are super important to understand how they do their job for us. They work so hard in each organelles. So this microscopy is non-single molecule microscopy, and with the pointless concept, if you look at the painting, you can see women, umbrella, children, or dogs, but actually, if you zoom in, they are all dots. With this concept, we can generate super resolution with just to find out to minimize the distance between the virtual emitters and the point square function. So precisely, we can localize those virtual emitters. That is a massive amount of emitters in the image, but finally, we can generate super resolution for visualization of cellular organelle level metabolic activities. For example, the magenta color are from the mitochondria, cyan color are protein enriched of cellular organelles, yellow color are from the lipid droplets. We can see how they interact with each other under the disease status or in the aging processes, even cluster these different chemical compositions in different subgroups of these lipid droplets, because lipid droplets can be cholesterol enriched or triglycerides enriched. So the most important part is the metabolic dynamics on top of these label-free technology, how we can see the newly synthesized molecules such as new protein, new fat molecule, or new DNA, new RNA, and carbohydrates such as glycogen. 2SS is the one that we can provide such kind of information. So it is integrated on top of the multimodal imaging system. The reason is fluorescence probes are so big, and for small metabolites, such as glucose on top or amino acids on top, they are so small. If we label with fluorescence probe to visualize them, it's not ideal. The fluorescence probe will perturbate the function of small metabolites. So here, our idea is to attach a single atom to generate a chemical bond. That chemical bond can generate a Raman signal that allow us to find out where is the newly synthesized molecule. So the favorite deuterium molecule I'm going to talk about today is found by Harold Urey. There is a extra neutron inside, which makes this heavy hydrogen heavier. Heavier hydrogen will be incorporated into the small metabolites first. For example, so the D2O molecule, you rip off an deuterium atom, then plug into the newly formed molecules, such as new lipids, protein, DNA, RNA, carbohydrates. In the new molecule, you can see a new chemical bond that is carbon deuterium, CD. Okay, what happened in the CD chemical bond when we review the Raman spectrum? We measure from natural biological system. No matter you measure it from plant or animal cell, you always generate this Raman spectrum. You can see fingerprint region have signal on the left side, and the cell silent region have no signal in the middle center side, in the center region, and also the CH stretching region have signals on the right side. So the cell silent region from 1800 to 2800, there's nothing until you generate a new signal in the cell silent region for newly synthesized molecule. Then we can simply pick up that signal to map out the newly formed molecule, including those protein, DNA, RNA, and the lipids. So you can see how these three colors merge together. Then this is a single cell that are doing mitosis, and you can see the magenta color are newly synthesized DNA, and the green color are newly synthesized the lipids, and the blue color are newly synthesized protein. So we can actually see those metabolic dynamics. For example, a brain is injured. So the injured brain, they can do healing process themselves. When the brain is healing, you can see the newly synthesized fat molecule accumulated on the left side. That's the injured brain, but on the right side, the naive brain doesn't have that level of newly formed fat molecule. This method also can allow us to visualize the tumor metabolic dynamic, metabolic heterogeneity, because tumor cells have a higher metabolic activity. We can visualize them by those enriched CD signal, because of the newly synthesized molecule are all deposited mainly in the tumor in the brain. So we can simply find out where is the tumor. And this technology can be also expanded to visualize, for example, glucose, amino acids, fatty acids, choline acetate, dopamine, or neurotransmitters. These small metabolites can also label with the deuterium molecule to generate the new chemical bond. And then we can see how the glucose derived, for example, the glucose derived lipids or glycogen or protein looks like, and it can be also 3D or time-lapse video recording. Okay, so these are telling us that we can see when, where, which cell, and how much they synthesize new molecules, new fat or new DNA or other molecules such as protein or glycogen. And this can be also in live cell or live animal. You can see a C. elegans is dancing, but you can do video recording to see this dancing C. elegans, where they synthesize new molecule, new lipids, protein, or other types of molecule in the body. We can see the head portion have new lipids deposit occur. And this technology can be also applied to study how the diet can regulate our aging processes, how the different type of diet, for example, we can eat less and we live longer. So what happened when we eat less and live longer? What does the fat metabolism change in the body, in the brain? This is telling us that we can visualize, we can see how the fat molecule, those molecular level change can be different under the diet restriction. So DR here is diet restriction. We can see actually eat less can increase fat metabolism. So fat metabolizes even faster under the diet restriction. Female and male have very different metabolic activity during the aging process. When they become old, the female are more sensitive to those diet regulation, but the male are less sensitive, especially for high sugar, like high glucose, high sucrose, or high fructose. So eat more sugar. I think it's not very good for a woman who is aging. All right, so I'll finish my talk by these last few slides. It's about AMPK, which is regulating or upregulating the glucose fat uptake when the cellular energy is low. So this is important in the Alzheimer's disease case. But we did the mouse with Alzheimer's disease, that's the tau overexpressed the mouse brain. We observed an elevated amount or excessive amount of fat molecule, fat droplets deposit in the hippocampus region. Hippocampus region is important for memory formation, how we memorize stuff, we memorize things. So by stimulate or activate the AMPK metabolic pathway, we can see actually this accumulation of fat molecule can be rescued by this AMPK metabolic pathway activation. So this is really an important study that it has been accepted by Cell Metabolism, and you can see that paper very soon, and this month, I think. I want to summarize what we talked about: 3 technologies, 3 actually imaging platform. So the first platform allows us to see the diverse types of biomolecule, map out the molecular specificity. The second A part is for subcellular organelle level metabolic activity. It's super resolution technology. Bioorthogonal is the one that we can see the newly synthesized molecule, distinguish it from the older existing molecule. So it's called bioorthogonal microscopy. They can be combined to study subcellular resolution, multiplex, and metabolic dynamics. So I would like to acknowledge my group members and funding source, and thank you so much for your attention.
Great, Lingyan, so wonderful talk. Actually, I really want to know that how many fat I can eat, how many sugar I can eat. Yeah. So during my age, is that safe or not? Okay. Yeah. So let's welcome everyone go to the panel discussions. I think we still have some time. For discussions. I do have some questions for both of you. Actually for maybe I start for Lingyan's talk. Okay, so close, got you fresh in my memory. So Lingyan, so interesting research, and I see you found so many kind of backyard story with samples by this. As you see that there are a lot of difference from females and men, right? Yeah, in the studies. So is that can really this maybe this question is a little bit out of the box, is this lead by gene or lead by something else? I think men and women are all humans.
Yes, I think this is a very, very interesting and important question you asked, because female and male, it's in biological point of view, there are sex differences. So sex differences include mainly 2 different, for example, molecular. Maybe we can talk about these molecular level or even gene level. So this first is the chromosome, right? It's about the DNA. So that's the XY or XX. XX is for female, XY is for male. So that level of gene perhaps can really impact the female and male metabolic dynamics during aging processes. But another thing mentioned I did not mention in my talk, but we do mention in our research projects. When we would do experiment, we talk a lot about those non-chromosome, but just hormonal, right? Hormonal. So that means even a female body, you can inject male hormone. You can inject those male hormone to make it like behave more like a male metabolic activity. So that's 2 big direction we can study, we can explore to see the differences. And actually, exactly as you just mentioned, it's very understudied. Really need more people who are interested to involve, especially those PhD students who are interested in this topic. They could study either the chromosome-based or the hormonal-based, the differences between the male and the female, and how the fat metabolism can be different during the aging processes. So the fat in the brain, the brain is a fat-enriched organ. Almost 85% of the brain, they are like fatty tissues. So fat metabolism is extremely important. And I learned a lot from the Xiuyun Liu's talk. I think these topics is super important. How those even the CSF regular circulation
circulation, yes,
the circulation of CSF under those choroid plexus story, and also the cilia story. I think they are all connected actually. How these the genetically they can really modify those cilia or other secretion of CSF, and how they impact the metabolism in the brain. And the male and the female can really be different during these aging processes. So, and I thank you for your question. And I really don't have a conclusive answer. However, we are open to study.
Okay, great. Xiuyun, maybe we can follow this, Yeah, so actually, you use a lot of tools, a lot of, kind of new technology, try to help all these people. So, as you know, I was working for the soft electronics, right? Yeah. So what's in your mind? Is that all these kind of, soft electronic or some micro-needles, all these, new.
Definitely they will be very useful in the intensive care unit. Like Lingyan's talk was really interesting and very advanced. So now I know why Lingyan got like 四龙奖, I don't know the English name, got a very prestigious award. And then you are very popular in Tianjin University, Lingyan. I would tell you.
Oh, really?
Yeah. So yeah, everybody knows that. So as you can see, Lingyan developed very good tools to image the cellular level mechanism. And also Alice, you talk about the soft chips or soft sensors, soft sensor, variable sensors are very important in intensive care unit. For example, we have the patient lying there, they are very severe, and then we need to monitor them closely, continuously. So you need to know what is happening to his heart, what is happening to his lung and to his brain. And then currently, as I showed in that picture, you have all the equipment, a lot of wires connected to this patient. That is really inconvenient, and sometimes it will be very dangerous. For example, if the doctor comes to turn the patient to the other direction, you may drag some lines off, and that will cause a big problem. So if you have those kind of variable disease and LDD devices, that will be very helpful in intensive care unit. And I know some scientists are already doing very excellent job, and Alice, you are doing excellent job. Hopefully we can collaborate in the future, and also I really hope to collaborate with Lingyan as well to push advanced technology into the clinical side, to put them into the real clinical practice for the doctors to use.
I'm also extremely interested in Xiuyun's technology and research. Actually, we can discuss afterwards.
Definitely we will. Yeah.
So nice, to get, all this Tianjin University alumni to meet on the iCANX. Okay, I'm sorry.
Yeah, I think she left the meeting or what. Yeah, Lingyan, so you did your bachelor in Tianjin University, right? In biomedical engineering department.
I got my bachelor from the same department as you are, in the biomedical engineering.
That's right. So that's really a coincidence. So that while I know you are attending today's talk, I was really excited.
Yes, me too.
Yeah. So what we are doing actually, we are trying to use zebrafish, as I showed, a rat, to try to simulate the pathway of the CSF, and you will find like for the healthy brain and the hydrocephalus brain or like AD brain, the circulation of the CSF will be very different. Like for healthy people, the CSF like circulates naturally. But for like AD brain or for hydrocephalus brain, the CSF is moving slowly.
Oh,
and
wow.
then and then because CSF is very important to bring out the wastes, right? And to bring in the oxygen and nutrition. So that is very important. And then currently we are trying to use some transfer genetic liver fish to highlight the artery, to highlight the tubes, to see like microtubes, to see the CSF circulation pathway. But if you have like hi Alice, we cannot see you. Collapsed. I'm sorry.
Yes, I can.
We cannot see you, but we can hear you. I see. Yeah. Yeah, sure.
Yeah. Okay.
Definitely. Yeah. Thank you so much, Alice.
Thank you.
Okay, thank you, Alice. Thank you, Lingyan. See you later. Bye.
See you later. Bye-bye.
Happy Women's Day. Bye.
Yeah, bye-bye.
Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, and entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks all these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us. And it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
インホイルセンスはセンシングの技術、エッジコンピューティング、安定した接続性、電力の自己生成機能、この4つによって可能になるタイヤを用いたテレメトリーソリューションです。インホイルセンスはセンサーからのデータをリアルタイムで収集・処理し、タイヤと路面の間に起きる相互作用についてかつてないデータ活用を実現します。センシングデータはBluetooth を使用して車両とクラウドに接続された機器に直接送信、そしてディスプレイや警告灯に表示するために使用可能な形式に処理されます。こうしたシステムは電力供給が課題でした。そこで TDK はタイヤの回転を利用して電力を生み出す仕組みを開発しました。インホイールセンスを活用することで未来の車ではより高度な運転支援や自律走行の安全システムを実現することが可能です。Technology for the well-being of all people.
Attracting tomorrow. TDK.
祝你生日快乐！该吹蜡烛了，来，我帮你。啊！祝你生日快乐！生日快乐！
好漂亮的花，我很喜欢。
这是我的礼物，多层陶瓷电容器。
哇，这是多层陶瓷电容器吗？
失败了，没新意。那个我的也是啊。
哇塞，这个不是太阳诱电的多层陶瓷电容器吗？小型、大容量，从原材料开始研发，性能和质量都有保证。我最想要的就是这个了，太阳诱电的多。